A detailed explanation about coefficient of performance for refrigerators and heat pumps will be explained in this part. Before we construct the COPR, we have to look at the objective of the refrigerators. The objective of the refrigerator is to remove QL from the cooled space. Look at this figure. This is our refrigerator and it consists of four main components. The evaporator here is used to absorb QL, and this QL is the desired output. Due to the objective of refrigerator is to remove QL from the cool space. We want to make this space at low temperature as possible by removing this QL. And here, this is the compressor. So compressor need W net in to compress the refrigerant from evaporator to the condenser. So therefore, W net in is the required input. So now, back to the theory of coefficient of performance, where it is the ratio between the desired output and the required input. The COPR now is QL over W net. But what is W net equal to? From the energy balance equation, we know that W net is QH minus QL. By substituting this W net into COPR, now the COPR can be written in terms of 1 minus QH over QL minus 1. And since QH is always greater than QL, the COP can be greater than 1, but only when QL over QL is less than 2. Next is COP heat pumps. Again, we have to know the objective of the heat pump. The objective of heat pump is to supply heat or QH into the warmer space. So from the schematic diagram here, this is our HP heat pump. So heat pump is used to supply QH in order to warm a space by absorbing QL from the cool environment. So in order to supply this QH to the warm space, compressor need W net in. So this W net in is the required input, while the QH is the desired output. Back to the concept of COP, HP, it is the ratio between the desired output and the required input. Now the desired output of heat pump is QH, and the required input still W net in, same as refrigerator. But what is Q net equal to? Still same, since we are referring to the energy balance equation, the W net equal to QH minus QL. Therefore, COPHP become as 1 over 1 minus QL over QH. Since QL is always less than QH, COP is always greater than 1. As I said in the previous part of this topic, in the second law of thermodynamics, they have two main statements that we need to understand and remember. The first one is Kelvin and Planck statement. Did you still remember the meaning of the Kelvin and Planck statement? If not, please look back to the previous part of this topic. Here, closure statement is the second statement, the second law of thermodynamics. Closures conclude that it is impossible to construct a device that operates in a cycle and produce no effect other than the transfer of heat from a lower temperature body to a high temperature body. For example, here, this figure, we have a refrigerator. This refrigerator absorbs QL 5 kJ from cold space and removed to a warm environment at 5 kJ without having any work done on the system, or W net in equal to 0. And this system violates the closure statement of the second law, because closure said that it is impossible to construct a device that operates in a cycle produce no effect other than transfer of heat. So they must have another effect, which is unit in. It states that a refrigerator cannot operate unless its compressor is driven by an external power source, such as an electric motor. So therefore, they need a work to operate. This way, the net effect on the surroundings involves the consumption of some energy in the form of work, in addition to the transfer of heat from a colder body to a warmer one. To date, no experiment has been conducted that contradicts the second law. This should be taken as sufficient proof of its validity. Okay, next we will look at the perpetual motion machines. So any device that violates the first or second law is called a perpetual motion machine. And this perpetual motion machine is not related with the it is related actually with the previous heat engines and refrigerator as well as heat pumps. But since these machines violate the first law and the second law, it is called as a perpetual motion machine. And these perpetual motion machines have two types. The first type is ppm1. If it violates the first law, it is a perpetual motion machine of the first type, or ppm1. While if it violates the second law, it is a perpetual motion machine of the second type. My question is, what does the first law of thermodynamics tell us? Please recall back the meaning of the first law. And what does the second law of thermodynamics tell us? If you cannot answer both, please look back at the first video or your lecture notes. Okay, here we have two figures that show to us the type of perpetual motion machine. On the left side, it is ppm1, a machine that violates the first law of thermodynamics. Why does this system violate the first law? The first law tells us that energy is neither created nor destroyed, isn't it? We cannot create energy or destroy the energy. But this system shows us that energy can be created. That's why this machine violates the first law. So how does this machine operates? By creating an energy. Now look at here. This is the system boundary. Inside the boundary, they have four main components: boiler, pump, condenser, and turbine. If we look at these four components, it looks like heat engine, isn't it? We have boiler, pump, condenser, and turbine. We know that condenser is used to release the heat to the environment. Therefore, they have Q out here. Turbine is used to produce work out. Pump is used to pump the working fluid to the boiler, and they need W in, right? But here, boiler. How does the boiler operate without having Q out? That is the main question that we need to answer. However, without having any Q in, the system still can be operated from this turbine and generator. We know turbine is used to produce work and the generator is used to deliver the W net out and to heat or to give power to the resistant heater in order to boil the water here. So that means generator create an energy for boiling the water. And this ppm show to us it violates the first law. So therefore, they call this kind of system as perpetual motion machine number 1. Next, look at the second figure. This second figure shows us the perpetual motion machine that violates the second law of thermodynamics or ppm2. They have a system boundary, still same with the ppm1. So inside the boundary, they have three components. The first one is boiler, second is pump, third is turbine. In the boiler, it receives Q in from surrounding, from the source to boil the water. And the working fluid flow from the boiler to the turbine in order to make W net out. Then the working fluid continue flows to the pound without having any heat release between turbine and pump. So from here we know that it violates the second law of thermodynamics. So they must have a component here that used to release the heat to the surrounding. So therefore, this kind of system is called PPM2, Perpetual Motion Machine number 2. Okay. Okay, so we have done for the first half of the second law of thermodynamics. For the second half, we are going to talk or discuss about reversible and irreversible processes. So every process, they have two types. The first type is reversible, a process that can be reversed without leaving any trace on the surrounding, and irreversible process, a process that is not reversible. The two familiar reversible process is shown in this figure. The first one is frictionless pendulum, and second is quasi-equilibrium expansion and compression of a gas. So all the processes occurring in nature are irreversible. As I explained at the earlier of this topic, water flows from uphill to downhill. So why we are interested in reversible processes? First, they are easy to analyze. Second, they serve as idealized models to which actual processes can be compared. So here, reversible means a process that is created by human, while irreversible process is a real process occurring in nature. And some processes are more irreversible than others. So we try to approximate reversible process. This is why. Because reversible processes deliver the most and consume the least work. This is why we are interested in reversible processes. We want to get more output and consume least input. For example, for the slow processes or reversible process, the pressure distribution is consistent. As well as during the compression process, the pressure distribution also consistent compared to the B, irreversible process. There are several factors that cause a process to be irreversible, a process that cannot be reversed. And the factors that cause the process to be irreversible is called irreversibilities. They have several factors or several irreversibilities. For example, friction, unrestrained expansion of gases, heat transfer through a finite temperature difference, mixing of two different fluids, electric resistance, inelastic deformation of solid, and as well as chemical reactions. For the reversible process or ideal process, none of these irreversibilities involved. So that's why the process can be reversed easily compared to irreversibles. Irreversible. So here, to make it clear, reversible is a ideal process, a process made by someone. We can adjust the process. We can control the process. While for the irreversible, it is occur in nature. We can control the process. Due to some factors or due to the irreversibility. Or in other words, irreversible process is a real process. Reversible is ideal process. So we are interested with the reversible because it is an ideal process. From there, we want to compare with the real one. We want to compare with the irreversible process. For the reversible processes or for the ideal processes, it is categorized into two. First one is internally reversible process, which means a process that is no irreversibilities occur within the boundaries of the system during the processes. And for the externally reversible processes, it is a process that is no irreversibilities occur outside the system boundaries during the process. Carnot cycle is one of the application, one of the famous example that is developed by the Nicholas Carnot for reversible cycle. Nicholas Carnot is one of the engineer, a French engineer that developed this cycle to show the ideal cycle, to show the reversible cycle. And the theoretical heat engine that operates on the Carnot cycle is called the Carnot heat engine. And this Carnot heat engine composed of 4 reversible processes. 2 of them are adiabatic heat transfer and the rest 2 are reversible isothermal heat transfer processes. So let's look at the mechanism of Carnot heat engine. We have a piston cylinder device, and for the first process, process 1 to process 2, it is reversible isothermal heat addition at high temperature. That is the name of the first process, reversible isothermal heat addition at high temperature. So during this process, pH is higher than TL to the working fluid in a piston cylinder device, which does some boundary work. Okay, so from the initial state, the piston expands from the initial state to the second state. So during this process, the temperature at the source is TH, and heat is absorbed by the substance. So that's why piston move outward, move to the right side. And during this process, the temperature is constant at TH. For the second process, process number 2 to process number 3, it is a reversible adiabatic expansion process. And during this process, the system does work as the working fluid temperature decreases from TH to TL. Why the temperature decrease? Due to the insulation. So if you look at the figure, the piston cylinder device is insulated. No heat can be transferred in and out of the system. At the same time, the piston is continuing move outward, which means the specific volume increase. Due to the increasing of specific volume, the temperature drop to TL. Okay. Third process, third process is the system. The system is brought in contact with a heat reservoir at TL lower than TH, and this process, process number 3 to number 4, is called as reversible isothermal heat exchange or heat transfer. Why? Because during this process, the piston cylinder device is no more insulated. So heat is transferred out from the system to the environment. And the piston start move inward, start move to the left side. And during this process, the temperature is constant. Why it is constant? Even the heat is transferred out of the system. The reason is during process 3 and 4, piston is compressed to the left side. Once it is compressed, temperature will increase, isn't it? But during this process, the boundary of the system is not insulated anymore. Some of the heat will release, and due to the phenomenon, the temperature remain constant. Okay, and finally, the last process is called a reversible adiabatic compression process. And during this process, process 4 to process 1, the boundary of the system is insulated again. No heat can be transferred in and out. And piston keep moving inward, keep moving to the left. And during this process, the temperature increased from TL to TH. Why? As I said just now, during the compression process, temperature will increase. But for this last process, the system is insulated. No heat can be transferred in and out. So the temperature keep inside the system. The heat keep inside the system. Cannot be released. Cannot be released out of the system. So therefore, the TL go up to TH. Okay, so that's the 4 processes in the Carnot heat engine. So here they have 2 principles for the Carnot heat engine. The first one, The efficiency of an irreversible heat engine or real heat engine is always less than the efficiency of a reversible one or ideal one operating between the same two reservoirs. And second principle, the efficiency of all reversible heat engines, the ideal one operating between the same two reservoirs, are the same. So both principles can be the both principle is shown in the figure. So let's look for the first one. We have 1, 2, 3 heat engines. For the first heat engine, it is irreversible heat engine, real heat engine, number one. For number two, it is reversible heat engine, which is ideal heat engine. Okay, 1 and 2, they are operating between the same reservoir, right? Between the same two reservoirs. The source is TH and the sink for both is TL. Okay, so the Carnot said the efficiency of an irreversible heat engine or heat engine number 1 is always less than heat engine number 2, reversible. So eta for the real heat engine always less than eta of the ideal heat engine that are operating between the same two reservoirs. For the second principle, it is in between heat engine number 2 and heat engine number 3. Heat engine number 2 and heat engine number 3 both are reversible heat engine, the ideal heat engine, and they are operating between the same two reservoirs. So therefore, the thermal efficiency for both number 2 and number 3, reversible one, are same. These are the principle for the Carnot heat engines. The heat engines that operating using Carnot cycle. Okay, in the previous slide, we have learned 4 processes in a Carnot heat engines. For the reverse Carnot cycle, it is used for the refrigerator and heat pump. So if you look at this PV diagram, the process starts from state number 1, then go to the state number 2, number 3, number 4, and back to number 1. And the arrow is reversed compared to the Carnot heat engine. So this reverse Carnot cycle is used for the refrigerator and heat pump. Okay. The heat is absorbed from the surrounding to the system during process 2 and 3 at the bottom and released to the environment during process 4 and 1 at the top of this cycle. Okay, next, in order to determine the efficiency of the Carnot heat engine, we have to apply this proportional to the temperature concept. Okay. For a reversible cycle, for the ideal cycle, the amount of heat transferred is proportional to the temperature of the reservoir, where QH, the ratio of QH and QL is equal to the ratio of the temperature TH and TL. Only applicable for the reversible cycle or Carnot cycle. So now the thermal efficiency of heat engines that use Carnot cycle can be written as 1 minus TL over TH instead of 1 minus QL over QH. Okay. So For the reversible case of the Carnot heat engine, the thermal efficiency can be determined by using both equations, 1 minus QL over QH or 1 minus TL over TH. If, on the other hand, if the heat engines is not Carnot, then the thermal efficiency can be determined by using 1 minus QL over QH only. And please remember that. Then for the reversible heat pump and reversible refrigerator, we can change the Q to the T as well. For example, COPHP for the reversible, for the Carnot, it can be written as 1 minus 1 over 1 minus TL over TH for the heat pumps. And for the refrigerator that operating by using Carnot cycle, the COP can be determined both by using this equation or this one. Okay? And all of this equation, this one for the heat pumps, and this one for the refrigerator, only true for the reversible case. Please remember this. Please remember this. Okay? Only applicable for the case of Carnot or reversible. Other than that, we cannot use both. We can only use this one and this one. How do reversible and real system compare? Okay. The answer is the efficiency of reversible heat engine, such as a Carnot engine, is always higher than a real engine or irreversible engine. Then the COP of a reversible heat pump is always higher than a real heat pump or irreversible heat pump. And last one, the COP of a reversible refrigerator is always higher than a real refrigerator or irreversible refrigerator. So we have done for the second law of thermodynamics. Now I just want to share the summary of this chapter. The second law of thermodynamics states that processes occur in a certain direction, one-way direction, not in any direction. And a process will not occur unless it satisfies both the first and the second laws of thermodynamics. Bodies that can absorb or reject finite amounts of heat isothermally, temperature is constant, are called thermal energy reservoirs or heat reservoirs. And they have two, right? Source and sink. Please remember that. Work can be converted to heat directly, but heat can be converted to work only by some devices, special devices called heat engines. So if you want to convert heat to work, you need heat engine. The thermal efficiency of heat engine is defined as 1 minus QL over QH. Okay, this 1 minus QL over QH is for irreversible heat engine, real heat engine. Then for the COP refrigerator and COP heat pump, the performance equation is written in the is shown as slide. And then in the second law, they have two main statements. The first statement is the Kelvin-Planck statement, and it stated that no heat engine can produce a net amount of work while exchanging heat with a single reservoir only. And closure statement stated that No device can transfer heat from a cooler body to a warmer one without leaving an effect on the surroundings. And any device that violates the first or the second law of thermodynamics is called a perpetual motion machine, PPM, F2, PPM1, and PPM2. Then a process is said to be reversible if both the system and the surrounding can be restored to their original conditions. Any other process is irreversible. Bracket, real. The effects such as friction, non-quasi-equilibrium expansion or compression, and heat transfer to a finite temperature difference render a process irreversible and are called irreversibilities. Or in other words, irreversibilities are the factors cause the process to be irreversible. Then the Carnot cycle is a reversible cycle, bracket, real, ideal, that is composed of 4 reversible processes. First two is isothermal heat transfer, and the other two is adiabatic expansion and compression process. Reversible adiabatic expansion process and reversible adiabatic compression process. Next, the Carnot principles state that the thermal efficiency of all reversible heat engines operating between the same two reservoirs are the same, and that no heat engine is more efficient than a reversible one operating between the same two reservoirs. And then these statements form the basis of establishing a thermodynamic temperature scale related to the heat transfers between a reversible device and the high and low temperature reservoirs by QH over QL for the reversible process equal to the TH over TL. And therefore, the QH over QL ratio can be replaced by TH over TL for reversible device, where TH and TL are the absolute temperatures of the high and low temperature reservoirs respectively. Okay, then a heat engine that operates on the reversible Carnot cycle is called a Carnot heat engine. The thermal efficiency of a Carnot heat engine as well as other reversible heat engines is given by 1 minus TL over TH. And this is the maximum efficiency of heat engine operating between two reservoirs at temperatures TH and TL can have. And then the COP of reversible refrigerators and heat pumps are given in a similar manner as shown in this slide. Again, these are the highest COPs a refrigerator or a heat pump operating between the temperature limits of TH and TL can have. Okay, so that's all for this topic. Thank you for your viewing and see you again. Assalamualaikum warahmatullahi wabarakatuh.